This talk is on capacity. We will talk about capacity of an operation and capacity of a process, which is composed of a set of operations. We talk about flow time, cycle time, and utilization, and then we a little bit expand on these concepts. Let's start with a simple example. To produce each batch of muffin, you prepare the material, then put the batch in the oven. There is only one oven, and the oven can handle one batch of muffin at a time. When the bake is done, your friend takes the batch out of the oven and does packaging and labeling. So we do have three sequential activities: preparation, bake, and package and label. We refer to them as operation A, operation B, and operation C. Three resources: you, oven, and your friend. Each activity takes some time. Estimating the time of each activity is in the framework of motion and time study, when you observe an operation in several random occasions, measure the operation time, average it, and you will assume that as the operation time. Or indirectly, may you use Little's law, because throughput times flow time is equal to inventory. In this situation, we assume flow times are given and each operation. In the first operation, it is 15 minutes, in the second, 20 minutes, and in the third, 5 minutes. Each day, we work 4 hours and 60 effective minutes are available in each hour, so we do have 240 working minutes per day. In this example, we saw capital resources. Oven is a capital resource. Fixed assets such as land, building, facility, machinery are capital resources. We also saw human resources. You and your friend are human resources. People such as engineers, operators, assembly line employees, chefs, customer service representatives are examples of human resources. So we saw activities or operations and resources. Each activity may require one or more resources. Each resource may be allocated to one or more activities. In the example we had, each resource was allocated to only one activity, and each activity needed only one resource. But we may have a resource allocated to several activities, and also a specific activity may require several resources. For example, a resource such as a baker may be used for several activities such as mixing, kneading, and so on. And an activity like loading an oven may require several resources such as the baker and the oven. Resource unit could be a single resource like you, your friend, like a baker, like a chef, like a mixer, like an oven, or it may be combination of several resources which perform like a unit. For example, all the people and equipment in an operation room, in an emergency room, they all together work as a resource unit. So as long as concepts are concerned, we said resources are divided into capital resources and human resources. A resource may be allocated to a single activity or several activities. One activity may require one single resource or several types of resources. A resource unit may be a single resource, like a baker, or it may be a combination of resources which they all together perform like an integrated resource unit. Example is an operating room. We have these operations, these resources, and these flow times at each operation, and we want to compute capacity of each operation. The first operation takes 15 minutes. 1 hour is 60 minutes. 60 divided by 15 is equal to 4. Therefore, the first operation's capacity is 4. Capacity of the second operation is 3. Capacity of the third operation is 12. Capacity of process is the capacity of smallest component of that process. Here, oven can produce only 3 units at a time. Therefore, the whole process can produce only 3 units at a time. So if I have several consecutive sequential operations in a process, capacity of the process is equal to minimal of the capacity of each operation. Here I have 3 operations. The first operation capacity of 4, second 3, third 12. The minimum of these 3 times is 3. Therefore, the capacity, the minimum of these 3 capacities is 3. Therefore, the capacity of the process is 3 units per hour. Every 60 minutes, 3 units may enter, pass, and leave the process. So 60 minutes, 3 units pass the process. Every 20 minutes, 1 unit pass the process, and we call it inter-arrival time or inter-departure time or cycle time of the process. The process that we considered here has capacity of 3, and every 20 minutes 1 unit of product goes out. It doesn't matter if we compute the capacity per hour or per minute. For example, here every 15 minutes we produce 1 unit of product. So every minute we produce 1 over 15 units of product. Here every 20 minutes we produce 1 product. Therefore, every minute we produce 1 over 20 units of product. Therefore, if I'm talking about capacity per minute, capacity of the first operation is 1 over 15, capacity of the second operation is 1 over 20, and capacity of the third operation is 1 over 5. Out of these 3, 1 over 15, 1 over 20, and 1 over 5, the minimal is this one. So the capacity of the process is 1 over 20 products per minute. 1 over 20 products per minute. Process capacity is minimal of these 3. 1 over 15, 1 over 20, and 1 over 5, which is 1 over 20. Each minute we produce 1 over 20 units. In 20 minutes we can send out 1 product. 20 minutes is inter-arrival time, inter-departure time, or cycle time. So given this process, how long does it take to produce 1 batch of muffin? In formal term, what is the flow time of producing 1 batch of muffin? what is the flow time of this process. So this process has three components, 15 minutes, 20 minutes, and 5 minutes. Therefore, the flow time is equal to summation of these three, which is 40 minutes. It takes 40 minutes to produce 1 unit of product. But not every 40 minutes one product goes out of the process. As we saw, every 20 minutes one product goes out of the process. So flow time is 40 minutes, while cycle time is 20 minutes. And I will explain more on this. How often a batch of muffin exit this process? In formal term, what is cycle time of this system? You prepare a batch of muffin in 15 minutes and you are ready to put it into the oven. When you put it into the oven, for example in minute 15, you will start the next batch and it takes you 15 minutes to complete it. Therefore, at minute 30, you are done with the second batch. However, the oven is not done. You put the first batch into the oven at minute 15. It takes the oven 20 minutes to do its job. Therefore, oven is done in minute 35. Until minute 35, you cannot put anything into the oven. So if you are finished at minute 30, you should wait for 5 minutes and then put the next batch into the oven. I have pictured the process here. This is the first batch. It takes you 15 minutes to complete it. At minute 15, you put it into the oven. And then you start the second batch. But here, the oven is not done yet. You need to wait until minute 35. At minute 35, your friend take the batch out of the oven and start processing it. And it will finish it at minute 40. Before going further, here is the flow time. 15 minutes, 20 minutes, and 5 minutes. When we add them together, it is 40 minutes and it's our flow time. So for the first batch, it takes flow time to go out of the process. But for the second batch and the other batches, it takes cycle time. And we will see it here. So at minute 35, at minute 30, you are done. You should wait until minute 35, and then at 35, you put the next batch into the oven. It will be in the oven until minute 55. But at minute 35, you can start the next batch. You are done at minute 50, but you need to wait until 55. At 55, your friend take the batch out of the oven. Now, oven at 55 is available. You put the next batch. And then you will start the fourth batch and you are done at minute 70. But you need to wait until minute 75 for the oven to be done. At 75, your friend takes the batch out and you can put the next batch in. Your friend completes its job at minute 80 and then the last batch is done in minute 100. So for the first batch to go out of the process, it takes 40 minutes. For the other batches, it only takes 20 minutes. Cycle time is 20 minutes, except for the first batch. Oven is the bottleneck. Batches exit the oven every 20 minutes. You also put the batches into the oven every 20 minutes. You put the first batch in minute 15, but then you need to wait until minute 35 to put the second batch, 55 to put the third batch, 75 to put the fourth batch. Let's look at the process once again. First batch, you complete it, put it into the oven, start the next batch. Oven is busy until 35. Then you could put the next batch. Oven is done at 55, you are done at 50, you need to wait 5 more minutes. Oven is done 20 minutes later, you need again wait for 5 minutes, and so on. Every 20 minutes, one batch goes out of the process. If I have 3 consecutive operations, one takes 15 minutes, the other 20, the last one 5, cycle time is maximum of these 3, which is 20. Cycle time is 20, maximum of flow time of each operation. But capacity is equal to the minimum of the capacity of the 3 operations. How many batches can be produced per day? Case 1 is starting from 0. So when you start your process, nothing is available there. It takes you 40 minutes to send the first batch out. So you do have 4 times 60 equal to 240 minutes. But it takes 40 minutes to send the first batch out. Therefore, 40 minus 240 is 200 minutes. You have 200 minutes, and it takes 20 minutes to send out any other additional batches, which is 10. 1 plus 10 is equal to 11. So the capacity of this process per day, if you start from scratch, if everything is empty, you should start with the first batch. No inventory is available in front of second operation and third operation. Then the capacity is 11 batches of muffin per day. Now let's talk about a second situation where at the end of the previous day we put 1 unit of work in process in front of each operation. Suppose it's not muffin to lose its quality if it is waiting there over the night. Suppose it's a oven for painting a pod. So in this case, if each operation has 1 unit of work in process in front of it at the beginning of the day, it takes only 5 minutes to produce the first product. And then we have 240 minutes minus 5, which is 235. And then every 20 minutes, we produce a new product. Therefore, there will be 11.75 products per day, and 1 was here. Therefore, the total production is 12.75. I gave this second example just to see the difference between the situation where we have inventory in front of each operation at the beginning of the next period and the situation where we should start from scratch. Now we want to discuss the concept of utilization in a fully utilized process. In a fully utilized process, utilization of the process is 100%, but utilization of different operations may be less than 100%, and I will explain it in a minute. Capacity or maximum throughput, we talk about that. In the example, we saw that capacity or maximum throughput of our system was 3 units per hour, or 1/20 units per minute. The flow time was 40 minutes, which was summation of the flow time of the three operations, 15 plus 20 plus 5. Cycle time was 20 minutes, which was the processing time of the bottleneck operation. So the capacity, because every 20 minutes we can produce one product, the capacity is 1 over 20 product per minute. 1 over 20 per minute. If I multiply this by 60, that would be per hour. 60 times 1 over 20 is 3 per hour. And because I work 4 hours a day, if I multiply 3 by 4, then I will get 12. Capacity of this process is 12 per day. By now we should have understood the following concepts. Flow time, what is flow time? Cycle time, capacity, and utilization. What is utilization for the oven? Oven is always working. Every 20 minutes, one batch of muffin comes out. Utilization of oven is 100% or 1, because the oven can produce 3 units per hour and we are producing 3 units per hour. So at full capacity, utilization of oven is 1 or 100%. In each 20 minutes, you only work 15 minutes. For 5 minutes, you wait for the oven. Therefore, your utilization is 15 divided by 20, which is 0.75 or 75%. In each 20 minutes where the oven is working at full capacity and you are working at 75% of capacity, your friend only works 5 minutes. Therefore, for your friend, his utilization or her utilization is 5 divided by 20, which is 25% or 0.25. We computed utilization of each operation based on flow time, activity time, operation time. However, usually utilization is computed based on capacity. But they both give the same results. We will see utilization of 3 operations when we compute it based on the capacities would be exactly the same as the numbers that we got based on flow times, based on operation times. We already know that the capacity of the first operation is 4, capacity of the second is 3, and capacity of the third is 12. Therefore, the process capacity is equal to the minimum of these 3 numbers, which is 3. Process capacity is 3. Now we can compute utilization of the first, second, and third operations. Process capacity is 3. Capacity of the first operation is 4. Therefore, utilization is 0.75 or 75%. Capacity of the second operation is 3 and it produces 3 per hour. Therefore, utilization is 1 or 100%. Capacity of the third operation is 12, but it only produces 3 per hour. Therefore, utilization is equal to 3 divided by 12, which is 0.25 or 25%. So, utilization is 0.75, 1, and 0.25, which is what we have already got. No operation can perform at 100% capacity. Let it alone that some people say we are performing at 120% of capacity. We will discuss it later. Suppose we have two ovens. In case when we had one oven was the bottleneck. Okay, our production is limited by the capacity of oven. Let's buy a second oven. Let's increase the capacity of the bottleneck. Let's elevate the capacity of the bottleneck by increasing the size of the bottleneck from one oven to two ovens. Still, it takes 20 minutes for each flow unit to pass through this operation. We can say here that we have a resource pool of two ovens which handle operation B. Processing time is 20 minutes. There is no change in it. So capacity of each of these units is 1/20, right? But we have two units of these resources. See, the number of units is equal to 2. If capacity of one of them is 1/20 flow units per minute, capacity of two of them is 2 times 1/20, which is 1/10 per minute. That is the capacity of this operation, 1/10 units per minute, or if I multiply it by 60, that would be 6 units per hour. Now we want to compute the new capacities and new cycle time. Here in the second operation, we know that because the capacity is 0.1 per minute, therefore each 1 minute 0.1 product leave the system, and 0.1, if we add 10.1 together, that would be 1. Therefore every 10 minutes 1 product leaves oven operations. Cycle time for this operation is 10 minutes. Now we define a new concept. Resource pool is a collection of interchangeable resource units, first oven, second oven, that can perform exactly the same set of activities. They both are able to do operation B. So now we have a new process. 15 minutes in operation A, 20 minutes in operation B, 5 minutes in operation C, but we doubled capacity of operation B. Capacity of each resource unit is 1/15 per minute, 1/20 per minute, 1/5 per minute. But we have one resource unit in the first operation, so it remains. But we have two resource units in the second operation, so it is changed to 1/10, and in the third operation it remains 1/5. 1/15, 1/10, 1/5. The minimum number here is this one. 1/15 is smaller than 1/10 and smaller than 1/5. Process capacity is 1/15 per minute. Flow time is still 20 plus 15 plus 5, which is 40. There is no change in flow time. But capacity is changed. It is 1/15 per minute. In other words, every 15 minutes, one flow unit leaves the system. In the previous situation, cycle time was 20 minutes. Here it is 15 minutes. process capacity is 1/15. Every minute 1/15 units are produced. So in 15 minutes 1 unit is produced. Or you may say capacity is 1/15 per minute, so it is 60 times 1/15, which is 4 per hour. 4 per hour, an hour is 60 minutes, divided by 4 is 15. Every 15 minutes, 1 unit of product. By having 2 ovens, flow time remains the same. Capacity, it doesn't move from 3 to 6. It doesn't increase from 3 to 6 because capacity of oven was 3. We doubled the oven. However, the capacity of the process didn't go from 3 to 6 because bottleneck shifted from oven to the first operation. Therefore, capacity, instead of going up to 6, it just went up to 4, from 3 to 4. And cycle time reduced from 20 minutes down to 15 minutes. These were the net impact of buying the second oven. And utilization of the 3 operations, the first operation utilization is equal to 1. The second operation, it is 67%, and the third operation is 33%. We can reach the same results by playing with the hourly capacity. First operation is 15 minutes. 1 hour is 60 minutes effective. 60 divided by 15 is 4. I do have 1 resource unit. Capacity at the first operation is 4 per hour. In the second operation, 60 divided by 20 is 3. Capacity of each resource unit is 3. But I have 2 resource units in this resource pool. And the capacity is 6, 2 times 3. And in the third one, 60 minutes divided by 5 is 12. And I have 1 resource unit. Therefore, the capacity of that resource unit, the capacity of that operation is 12 per hour. And therefore, the capacity of the process is equal to minimum of these 3 numbers, which is 4. The first operation is the bottleneck. Each hour, the system can produce 4 units, and 1 hour is 60 minutes. Therefore, 60 divided by 4 is 15. Every 15 minutes, we produce 1 unit, which is the flow time at bottleneck resource, inter-arrival time, inter-departure time, or the cycle time is 15 minutes, where the process works at 100% capacity. Utilization for the first operation is 1, for the second is 67%, and for the third one is 33%. Now let's discuss a very important concept of resource pooling. In the first setting, when we had 1 oven, you were idle 5 minutes per 20 minutes. In 1 hour, you were idle 15 minutes. Your friend in 1 hour was idle 45 minutes, because every 20 minutes 1 batch of muffin goes to him and he works or she works on it for 5 minutes. In 1 hour, 3 batches goes out and he works only 15 minutes out of 60 minutes. In the second situation, capacity was increased to 4 by doubling the capacity of oven. The bottleneck shifted to you. You were busy 100% of time, but your friend was busy only 33% of time. Now we want to cross-train you and your friend, such as both of you can do both operation A and operation B. Now I have two human resources, and on each flow unit they are busy 15 plus 5 equal to 20 minutes. So I have two human resources and I have two capital resources. Human resource is busy 20 minutes on each flow unit. Capital resource is also busy 20 minutes on each flow unit. Capacity of one human resource is 60 divided by 20, which is 3, but I have two human resources, capacity is 6. Capacity of the capital resource, which is oven, is 6. Capacity of both of them are equal. They both are bottleneck. Resource pooling is very good, but when it reaches to having several resources working at 100% capacity, that's not good. It is risky. Because when utilization is 100%, systems can easily end up with a lot of raw material or a lot of people waiting in the line. We will discuss this concept later, but as I mentioned before, no system can work for a long time at 100% capacity. And if there are several resource pools in a system which they all work at 100% capacity, then the system is not in a very safe mode. Each of these links may break. But the concept of cross-training, the concept of mixing different resources into each other, train them to be able to do several types of activities, is one of the most important concepts in operations management. It can increase throughput and it can reduce flow time. The main idea is here. If we have two resources and they are working on different tasks and they cannot combine their tasks, one resource cannot do the job of the other resource. In that case, sometimes this resource is busy and several people or several units of product are waiting for it, and the other one is idle and nothing is there. So if these two resources are not pulled together, the blue resource cannot take this product or this customer and handle it, while this resource has waiting line and this one is idle. This resource cannot help this one. It is a power operational concept which significantly not only affect flow rate but also flow time. Now let's go through this practice. We want to know cycle time and we want to know capacity. Here we have four resources: Christine, her roommate, mixer, oven. And these are four sequential operations. Capacity per hour is 60 divided by 8, 60 divided by 3, 60 divided by 6, and 60 divided by 10. Out of these four numbers, this one is the smallest. Therefore, capacity of the process is 6 per hour. It means cycle time is equal to 60 divided by 6 which is 10 minutes. What is flow time? Flow time is 8 plus 3 plus 6 plus 10, which is 27. Flow time. So each flow unit needs 27 minutes work, but every 10 minutes we can send out one flow unit. Utilization, this one capacity is 7.5, this one capacity is 20, this one capacity is 10, this one capacity is 6, and process capacity is 6. So these are utilization of these operations. This is 1, this is 0.6, this is 0.3, and this one is 80%, 0.8. Now suppose, because the bottleneck is oven, we have 2 ovens. Again, these are times at each operation. 7.5 remains the same, 20 remains the same, 10 remains the same, but here we have 2 ovens. Therefore, capacity is 2 times 6, which is 12. 7.5, 20, 10, 12. By doubling the capacity of oven, capacity of the process doesn't go to 12 because bottleneck shifts from the last operation to the first operation, which is Christine. Process capacity now is 7.5. Flow time still is equal to 8 plus 3 plus 6 plus 10. Each hour you produce 7.5 units. Therefore, 60 minutes divided by 7.5 is equal to every 8 minutes, 1 unit of product goes out. Capacity of the first one is 7.5, second one 20, third one 10, fourth one 12. Capacity of process 7.5, 7.5, 7.5, and 7.5. These are utilization of different operations. Now let's look at a third scenario. We have one mixer, 2 ovens, and we have cross-trained our human resources. We have cross-trained Christine and roommate. They have become interchangeable resource units. We have done resource pooling. 2 human resources, we have cross-trained them. Now they both can do both activities, first activity or second activity. The time of the first activity was 8, the time of the second activity was 3. Our human resource has a unit load of 8 plus 3 minutes, and in 1 hour we have 60 minutes and the load is 11 minutes, and we do have 2 resource units in our resource pool. Here we have 60 divided by 6, and we have 1 resource unit. Here it is 60 divided by 10, and we have 2 ovens, 2 resource units. The first resource pool, which is human resource pool, can produce 10.9 flow units per hour. Mixer can produce 10 units per hour, and oven can produce 12 units per hour. Out of these 3, mixer is the bottleneck. Flow time is still 8 plus 3 plus 6 plus 10, which is 27 minutes. Cycle time, each 60 minutes, we can produce 10 units, so cycle time is 6 minutes. Here, because I have only one resource unit, I could see 6 here too. This 6 is the same as that 6. Utilization of the 3 resources, the capacity of this one is 10.9, capacity of this one is 10, and capacity of this one is 12, but we can maximally produce 10 units. And as we will discuss it later, no resource can perform at 100% capacity. Therefore, the best we can do is to produce 10 units per hour, 10 units per hour, 10 units per hour, and 10 units per hour. This is utilization of human resources, this is utilization of the mixer, and this is utilization of the oven. We can repeat the same computations per minute. Over there we did it per hour. We can do per minute. I have shown in several occasions that doing per minute, per hour, per day reach the same results. What I like is to do my computation based on the time unit given to me. Here, time unit given to me is minute. This is 8 minutes. This is 3 minutes, 6 minutes, and 10 minutes. So when I talk about capacity, I simply divide 1 by each of these. 1 over 8, 1 over 3, 1 over 6, and 1 over 10. This is the capacity of each of these resources per minute. Out of these 4 numbers, the smallest is 1 over 10. Therefore, oven is the bottleneck. My capacity is 1 over 10 per minute. In 1 hour, it is 1 over 10 times 60, which is 6 per hour. But if I just divide 1 by those 8 minutes, 3 minutes, 6 minutes, and 10 minutes, I will get capacity. If these numbers were hours, 8 hours, 3 hours, 6 hours, and 10 hours, then 1 divided by each of them will give me capacity per hour. 1 divided by TP is capacity per the same time unit that TP is stated. Flow time is still 8 plus 3 plus 6 plus 10. Cycle time, because here is the bottleneck, and because the bottleneck is a single resource unit, therefore cycle time is 10. I don't need to do any computation. If you want a computation, because capacity is 1 over 10, each minute you produce 1 over 10, therefore after 10 minutes you produce 1, and therefore cycle time is 10 minutes. Utilization is 1 over 8 capacity of the first one, 1 over 3 capacity of the second one, 1 over 6 capacity of third one, and 1 over 10 capacity of the bottleneck. Production is equal to, maximum production is equal to capacity of the bottleneck, which is 1 over 10. 1 over 10, 1 over 10, 1 over 10. These are utilizations. And here are the computations, capacity. Now suppose I have 2 ovens. Again, capacity here is 1 over 8 per minute, 1 over 3 per minute, 1 over 6 per minute, 1 over 10 per minute for one resource unit, but because this resource pool contains 2 resource units, therefore capacity of oven is 2 times 1 over 10, which is equal to 2 over 10. Out of these 4 numbers, 1 over 8 is the smallest. Therefore, capacity of the process is 1 over 8 per minute. And if I multiply it by 60, I will get 7.5 per hour. Flow time is still 8 plus 3 plus 6 plus 10. Cycle time, 1 minute, we produce 1 over 8. Therefore, after 8 minutes, we produce 1. And this 8 can be read from there too. As long as only one resource unit exists in a resource pool, then cycle time is equal to TP. TP for Christine is 8. Cycle time is equal to TP of the bottleneck if I do have only one resource unit in the resource pool of my bottleneck. But if you don't want to care whether you have one resource unit or 10 resource unit, you just have the capacity of bottleneck, which is 1 over 8 in 1 minute. You can produce 1 over 8 product. Therefore, after 8 minutes, you can produce 1 product. Utilization is 1 over 8, 1 over 3, 1 over 6, 2 over 10, and the process capacity is 1 over 8, 1 over 8. The last scenario, when we do have cross-training and create a new resource pool called human with 2 resource units. They are not Christian and roommate anymore because they can do each other's job, so we refer to them as one type of resource unit. We do have 2 resource units of this type. Capacity of this one is 1 over 11. Capacity of this one is 1 over 6. Capacity of this one is 1 over 10. Out of these 3 numbers, this one is the minimal. So capacity of the process is 1 over 6. Cycle time, 1 over 6 per minute. We need 6 minutes to produce 1 product, so cycle time is equal to 6 minutes. And I could have read it from here too. We are in page 19. You need to excel the previous 19 pages to be able to write the quiz. Now let's look at this problem. We produce 2 products, product A and product BC. Product A needs to go through operation A. Product BC needs to go through operation B first and then operation C. Both product A and product BC, they need to go through operation D and operation E. Operation A can handle 60 product A per day. Operation B and C are only for product BC and their capacity is 80 and 45 as I have depicted here. And operation D and E are needed for both products, product A and product BC. Capacity of E is 90 and capacity of D is 100. Which operation is the bottleneck? If the demand for product A is 50 units and demand for product BC is also 50 units per day. As long as product A is concerned, operation A is not bottleneck because the demand is 50 and this operation can handle 60 units per day. For product BC, operation B is not bottleneck because its capacity is 80 while the demand is only 50 for BC. But operation C has capacity of 45 while the demand for BC is 50. Therefore, operation C is bottleneck. We have 50A and 50BC, total of 100. D can handle 100 units of A and BC. It is not bottleneck, but E cannot handle 100 units of A and BC. The can handle only 90 units. Therefore, one bottleneck is here and the other bottleneck is there. Both stations C and E are bottleneck. This second part looks a little bit more difficult. Which one of the following is not correct? The utilization rate of station A is at least 75%. Look, we know that the maximum production of BC is 45. If this maximum reaches, if we produce 45 units of BC, here we cannot produce more than 45A, because 45 plus 45 is 90, and is the capacity of this bottleneck. However, we may produce 40 of BC. In that case, I can produce 50 of A. Therefore, production of A could be anything from 45 to 50. Because demand is 50, we want to produce 50 units, but if we produce 45 of BC, we cannot produce 50 of A, we can produce only 45. So the minimum production of A is 45. Capacity of this operation A is 60. 45 divided by 60. This is the minimal utilization of station A. 45 divided by 60 is 0.75 or 75%. Therefore, this one is correct. Utilization of station B is at least 50%. For product BC, demand is 50. We cannot produce more than 45 as this constraint states, as this bottleneck states. But if I want to produce 50 of A, I will not be able to produce more than 40 of BC. Therefore, production of BC is between 40 and 45. Station B's capacity is 80. Minimal production is 40. 40 divided by 80 is equal to 0.5. Therefore, the utilization rate of station B is at least 50%. Therefore, as we learned, A could be between 45 and 50, and BC between 40 and 45. Now let's go to the third question. The utilization of station B is at most 56.25. The maximum we can produce product BC is 45. Capacity of this station is 80. 45 plus 1.25. That is 56.25. So I did it manually. You don't need to be worried about how I computed this. It comes out 0.5625, which is 56.25. That's 56.25. Utilization of station D is 90%. We produce 90 units of these two products because demand is 100 and department E allows us to produce 90 units. Therefore, 90 divided by 100 is equal to 0.9 or 90%. So the answer to this question is none of the above. All of these answers are correct. And here are repetition of what I said. E, we can produce at most 90 of AA and BC. Based on C, we can produce at most 45 of BC. We may produce all combination of 50 AA and 40 BC to 45 AA and 45 BC. Station A at least 75%, station D 90%, station B 50% at least, station B 56.25% at most, and therefore all of the answers are correct.